reduce their privilege level, and compartmentalize them. So if you do take advantage of one service, if you do take control of one service, you can't spread easily, and that doesn't automatically mean a system compromise. So the first thing we did is we wanted to get services out of local system. I mean, if you have, no matter what you do, if you have a compromise in local system, it's game over in Windows. And so we wanted to get them to these low privilege accounts, local service and network service that we had introduced in Windows XP. A local service and network service, if you're not familiar with them, are additional service accounts, but they're dramatically less privileged than local systems. So for example, they're not members of the administrators group. They don't have all of the really super powerful privileges in Windows like TCB, create, token, debug, and all those different privileges. And so they really are closer to a standard user account. If you just compare Vista to XPSP2, 8 system services that used to run as local system now run as local service, and you can see the list over there. We also took 4 services that used to run as local system and dropped their privilege level, and now they run as network service. Furthermore, for new services in Windows Vista, we saw adoption of these low-priv service account consistently across the board, and almost half of them take advantage of a low-privilege service account. So this is really taking Windows services and dropping the privilege level among them dramatically. So that's the first part of service hardening. The next part was, many times services have configuration information that's specific to that service, and it's not really information that should be shared or accessible by just any other service on the box. And so we introduced this concept called the service SID. It's something that's implemented in Vista, and third-party applications that run on top of Vista can take advantage of it as well. But what it means is when your service starts up, you get an additional SID injected into your token that is a SID uniquely identified with that service. If you have multiple services in a service host, you get a SID for each one of those. Now what you can do with that SID is go use it in access control. And so for example, you can take, if you're the DHCP service and you have DHCP information in the registry that's really only meant for the DHCP service to modify, you can now go ACL that information to the DHCP service SID, and if another process is compromised, local service or network service, it doesn't have ACL permission to modify those resources. The next thing we introduced was a way for services to declare what privileges that they needed, and for the service control manager to automatically strip all the unnecessary privileges from their token. And so there's APIs that people can call to say, here's a set of privileges I'm going to use. If you have multiple services in a service host, the service control manager takes a union of those and puts it in there and strips away all the rest. Another thing you can do is we wanted to take services and really try to confine them down to their expected behavior. And so one of the ways that we did this was by putting network restrictions in. So if you have a service and the only thing you do is listen inbound on port 123, you can describe that and implement it, and it will be enforced by the firewall. And so if that process is compromised, that process won't be able to make outbound connections. And a lot of these restrictions and improvements that I've talked about are really process-wide. And so to really take maximal advantage of these things, we needed to go reorder and regroup the services in the shared service host of Vista, because even if you have 29 services in the service host that don't need TCP and one of them does, then they all get it. And so we went and reconfigured them, and you can see here there's a variety of different, basically flavors of service host processes that have various restrictions. And so if you have a service that you don't need network access and you can run as local service, you run in the local service no network service host. There's also varying flavors of things that have services, either network service or local service, that have a restricted set of network behaviors, or in some cases very restricted access to write to the file system, just very particular directories, but not broad rights to access the file system. And here's an example of the DHCP service in XPSP2, which was quite a big security effort by Microsoft, compared with the DHCP service in Windows Vista. So it used to run as local system and now runs as local service. It used to have 24 privileges by default, and now only has 4. It used to have a network identity, and what that means is that service could go authenticate on the network as the machine account of that box. And that allows it to basically have an authenticated user context, which, if that process is compromised, now it can go attack any other host on the network that needs an authenticated account. In Windows Vista, it doesn't have any ability to do that, so it goes off the box anonymously. It uses a fixed set of ports and also takes advantage of the service SID to compartmentalize access to the data that's unique to it. Automating proven techniques. So this was really about taking techniques that we know work, that we know can find security defects, and wiring that into the process and running those across the board. So I want to spend a little bit of time talking about SAL. It's the standard annotation language. And this is really a big technology that we use to improve the ability for tools to find defects. If you think about it, tools can only find so much information by just looking at source code. So for example, if you take a very simple line of code that says, assign this element of this array this value, is there a buffer overrun, buffer underrun here? You really don't know unless you know what the size of the buffer is and what that particular value of the array index is. And so the problem is that C and C++ code really doesn't have any way to easily identify that. SAL helps bridge the gap by allowing developers to annotate relationships between things and saying this element of this structure is really the size of the rest of the structure, or this second parameter is really the number of elements in the array that's passing the first parameter. It's not a brand new concept. If you've used RPC before, you're very familiar with these kind of concepts through IDLE. But what we did in Vista was we took all of the public APIs, added these annotations, and now when you run these tools against it, bugs will just pop out of it much easier than before. So this is kind of an example of how SAL works and how applying SAL. Imagine you have a very simple function that takes a buffer, takes a number of characters in that buffer, and then just fills that buffer with a character that you supply. Now clearly if the size of the buffer that you pass in doesn't correspond to the real size of the buffer, this thing will just walk up the end of the buffer and you have a buffer overrun. In Vista, if this function was there, a developer would see it and say, I have a string buffer, that means I need to annotate this function with SAL. The second parameter has a relationship that's involved with the first parameter. It says how many characters to write. So after they finish SAL annotating, it would look like this. And what you see in blue there is essentially a set of macros that the prefast and prefix tools will use when it analyzes the function. And let me walk through what this annotation is basically saying. So what it says is the underscore out, that's the prefix in the annotation. What that says is this buffer needs to be non-null because this buffer is going to be written to by this function. The second one is there is a length parameter. There's a length that this buffer has a fixed length, and that length is passed in by the cchbuff second parameter. And furthermore, that length is an element count, which means a character count in this case, versus a byte count. And this indicates which parameter actually communicates that length. So here's an example of security vulnerability in a very simple program and how these annotations can help tools find these issues. If you have Visual Studio 2005, it has a version of prefast built into it, and you could take this code, compile it in there, and what the compiler would tell you is, first of all, that there's a buffer overrun accessing the first parameter buff. The writable size is only 200 characters or 400 bytes, but actually 420 bytes might be written because this program was compiled for Unicode, so it tells you right away there's a buffer overrun here. The second one is, you can see there's a call to malloc, and this program doesn't check if that returns null or not. It just passes that value right into the function. And so it's telling you, it's finding a violation of the SAL constraint that says that buffer needs to be non-null in all cases. So here's two security defects that were found just in this particular code by putting a very simple annotation into it. And if you think about it, we're applying this to all of the APIs in Vista. So everybody that writes code on top of the platform will get the benefit of the smartness that these APIs allow the tools to be. So I don't know how many of you remember this buffer overrun. This was shortly after we shipped IE7 Beta 2. There was an advisory put out by a vulnerability researcher that says if you construct an HTML page that has it, you have a stack buffer overrun in IE. Workaround is documented by the finder. The net issue was there was a particular function path create from URL that had a buffer overrun in it. When a number of the people on the SWI team saw this vulnerability report come in January, after all of our efforts in Vista so far, this was pretty much the reaction of the people in our team. But it turns out when we went and looked behind what was going on, this bug had actually been found by prefast 2 months earlier. And it was sitting active in the bug database of Vista, ready to be worked on. Hadn't been fixed yet because it was just a beta going out the door. Hadn't been fixed yet, but it was sitting active in the bug database. And what I'm going to show you here is number one, how SAL helped us find this defect. And all of the text that's in this bug was automatically entered by the tool. So this is not a pen tester going through and saying, here's what's going on. This is the power that these tools have. So the first one that it says is there's a potential overflow using this particular parameter. It says it doesn't see anywhere where the size of this buffer is constrained in any way by the code. There's no if check that says if it's less than blah, blah, blah. It just says it looks like it's just passed in. The buffer is of max path, which is 260 elements. the SAL contract requires that there be a relationship between the buffer size and the buffer length that's passed in, and it doesn't see how that's indicated, and so it's telling you that there's a buffer overrun here. So we kind of look at this and we think, well, did SDL really succeed or fail in this case? So if you really walk backwards a little bit further, the first thing is, after the Zotob worm came out, that exploited a vulnerability in the PNP RPC interface. After we looked at the coding construct used behind that particular vulnerability, we realized our tools didn't find it, so we added that particular pattern to prefast and said, now it'll emit warning number 2015 when you run that tool on the code base. We changed our process to actually auto-file bugs based on that warning number. That IE bug, because of the SAL annotation, was caught immediately, and if we hadn't SAL annotated all these different functions, we wouldn't have found this defect. Furthermore, our internal fuzzing efforts reproed this exact issue just 8 days after the vulnerability report. When the browser crashed, users started sending these crash reports to Microsoft. Any crash report that comes to Microsoft that's caused because of a security defect, because the /GS flag terminates the process or what have you, security engineers and product team members, go look at those on a priority basis and try to understand, these are potentially real buffer overruns touching a customer in the wild. And so we went and actually found this exact bug through that channel. So we had 3 different ways to find this bug through the Vista process. So was I happy that we didn't have it fixed by beta? No, but I really think we would have had this bug fixed by RTM. The next area. So if you've been paying attention at all, you've seen that there's really been a very sustained attack going on across the board, not just Microsoft, but especially on Microsoft applications, targeting of parsers. And so it's not that you just go to a web page and it has a malformed JPEG and you get owned, or a bitmap, or an AVI movie file, or an animated cursor, or a font. It's really across the board. The volume of attack here is really quite incredible. And so we went to Jim Alton early on in the process and we said, if there's one thing you do in Vista, you have to get this parser story cleaned up. And so we embarked on a multi-pronged initiative to do that. The effort started by automating absolutely everything we could. So we have internal fuzzing tools that we think are as good as the external fuzzing tools. We took these tools and we identified all the different parsers that are on the attack surface for Windows and ran these tools against them. I think now we're up to 110 million different manipulations of files that are being run through these parsers and whatnot. For high-risk parsers that were particularly on the attack surface, particularly exposed, we have this extension to our fuzzers called DDL, or Data Definition Language. And what this allows you to do is to explain in an XML syntax more about the structure of the file format that you're going to fuzz. And this acts as additional intelligence and information that the tool can use to more intelligently target and fuzz the file format. And then for particularly hard targets, things that have a very complex format, things like EMF and HTML, we went after and developed smart fuzzers to go after those. In some places, we took this concept of code coverage. Clearly, it's not enough just to fuzz a particular parser. If you don't get any feedback from your fuzzing process, you really have no idea, are you just bouncing off the surface because of a checksum, or are you really getting deep into the parser? And so code coverage was one way we measured exactly what blocks and how deep were we able to go get in these parsers. Another way that code coverage helped was to make our fuzzing just that much more efficient. So for example, when we went to go fuzz JPEGs, we said, give us all your JPEGs, come one, come all, and we had a library of 19,000 different JPEGs that were the input to the fuzzing process. We went and analyzed the code coverage, the functional code coverage that these JPEGs got, and we actually were able to collapse this 19,000 JPEGs down to 47 JPEGs